Greetings and salutations. In this video, I want to talk about arc length, the total length of the curve, that is, how many steps you would have to take in order to traverse it from beginning to end. This is a concept you might be familiar with in R2, maybe from Calc 1. If so, you might recall the plan of attack. Like many concepts in calculus, we begin with an approximation. This time, we approximate the curve by many tiny line segments. And if we zoom in, we can use the Pythagorean theorem to calculate the lengths of these tiny segments. Then the total arc length, which we denote S, is the sum of all of these lengths. Then as we take the limit as delta x goes to 0, we get the following formula for arc length. Notice, though, that if x and y are components of a vector function, then this is just the length of that vector function's derivative. And so the arc length of a curve is just the integral of the length of the derivative of the original vector function. This fact is true not only in R2, but in R3, and in all dimensions. Let's see some examples of this. The first example I want to do is the circumference of a circle of radius r. And we know that the vector function associated to this curve is r of t is r cosine t comma r sine t. Of course, we need to bound t between 0 and 2 pi because we only want to go around the circle once. Then the derivative of this vector function is negative r sine t comma r cosine t. Then the length of the derivative is the square root of r squared sine squared plus r squared cosine squared, which of course is just r. And so by following through with this calculation, we can see that the arc length is 2 pi r, which of course is what we would expect to be the formula for the circumference of a circle of radius r. When working with a new formula, it's often useful to verify that it agrees with previously known formulas. For the next example, let's calculate the arc length of the graph y equals x to the 3 halves from the points 0, 0 to the point 4, 8. An easy vector function for this is just r of t is t comma t to the 3 halves, where t ranges between 0 and 4. And so now we calculate the derivative of the vector function and the length of the derivative of the vector function. This time when we integrate to calculate arc length, we're going to need to make a u substitution. Here we make the substitution u equals 1 plus 9/4 t, and then we integrate. Keep in mind that before we plug in the values for t, we have to first substitute that u equals 1 plus 9/4 t back in. And there we go. For the third example, let's move to R3, and let's calculate the length around one loop of a helix of radius 2. The helix will be given by the vector function 2 cosine t, 2 sine t, t, where t goes between 0 and 2 pi. Again, we calculate the derivative and then the length of the derivative, which happens to be square root of 5. Already we've arrived at an interesting fact, that when traveling along a helix, you are going the same speed at every point, even if your velocity is changing directions. And so we finish the example by integrating this speed with respect to time between 0 and 2 pi, and we get 2 pi root 5. Now, as we have seen, any curve can have many parameterizations. Sometimes the particle moves slower, sometimes the particle moves faster. So a good question to ask would be, is there a best parameterization to use? Now, while best is subjective and depends on the application, it would be useful to have a parameterization in which the particle moves 1 unit of distance for every unit of time. We call this the parameterization with respect to arc length. And here is how we reparameterize with respect to arc length. We first define an arc length function where when you plug in a time capital T, you calculate the distance you've traveled after that many seconds. This gives you your arc length as a function of time. Now, if you solve for t, you can get your time as a function of arc length. You can think of this function as a speed regulator. It's making sure the particle moves at exactly 1 unit per second. And we plug that function back into the original vector function. What we have then is the reparameterization with respect to arc length. As an example of this calculation, let's reparameterize the given helix with respect to arc length. We calculate the arc length function and find that s is equal to the square root of 13 times t. Then solving for t, we have t is equal to s over root 13. And so by plugging that into the original vector function, we have our reparameterization. Take a moment to check that a particle moving with this parameterization does have a speed of 1.